Hello. This will be a demonstration of Proposition 4 from Book 10 of Euclid's Elements, which requires us to find the greatest common measure of three commensurable magnitudes. This is just the logical extension of the previous proposition 10.3. In that one, we found the greatest common measure of two commensurable magnitudes, and we're just adding one more onto that. So instead of finding the greatest common measure of two commensurable magnitudes, we're finding that of three commensurable magnitudes. In this case, those three commensurable magnitudes will be A, B, and C, all of which are commensurable with one another. So A is commensurable with B, B is commensurable with C, and A is commensurable with C, so that the three of them altogether are commensurable with one another. And the task before us in this proposition is to find their greatest common measure. That is, the greatest magnitude, which measures A, B, and C, all three of them at once. We're going to begin by taking the greatest common measure of A and B, just the two of them on their own. We're going to call that D. D will be the greatest common measure of A and B. It will be the greatest magnitude, which measures both A and B. And we can, of course, find this magnitude D according to Proposition 10.3. Now, it is either the case that the magnitude D measures the magnitude C, or it does not. If it does measure C, then it's obviously a common measure, for it was made to measure both A and B. So if it happens to measure C, then it's clearly a common measure. And we know also that there will be no magnitude greater than D, which measures A, B, and C all at once. For if there were such a magnitude, then D would not be the greatest common measure of A and B, which we made it out to be. So if D measures C, then it is the greatest common measure of A and B. But if it does not measure C, then we at least know that the two of them are commensurable. For we know that A, B, and C, all three of them are commensurable with one another. So we know that there will be some magnitude which measures all three of them. And this same magnitude will measure the greatest common measure of A and B. That's what the porism of the previous proposition 10.3 tells us, that if a magnitude measures two magnitudes, it also measures their greatest common measure, so that because A, B, and C are all commensurable with one another, most importantly, that A and B are commensurable with one another, there will be some magnitude which measures the two of them at once, and this same magnitude will also measure D. But it was also made to measure C, so C and D will have a common measure. Now, because they are commensurable, we know that we can find their greatest common measure. We can do this again according to Proposition 10.3. We're going to find it and call it E. Now, E will be the greatest common measure of C and D. It is the greatest magnitude, which measures both C and D. Now, it is clear that E is a common measure of A, B, and C all at once, for it was made to measure D, and D was made to measure A and B. So a property of magnitudes tells us that E also measures A and B. But E was again made to measure C, so E measures A, B, and C all in common, so that E is a common measure of A, B, and C. Now next I say that it is the greatest common measure of A, B, and C. For if it is not, then there will be some magnitude F, which is greater than E, and which also measures A, B, and C. Now, because this magnitude F measures A and B, the porism of Proposition 10.3 tells us again that this magnitude F will measure their greatest common measure, which we found to be D in our first step, so that because F measures A and B, and D is the greatest common measure of A and B, F therefore measures D. But we also made F to measure C, so it measures both C and D, which again means, by the porism of Proposition 10.3, that it measures the greatest common measure of C and D, which we made to be E. So that because F measures both C and D, and E is the greatest common measure of C and D, F therefore measures E, so that F is therefore less than E. But this is contrary to how we made it. We made F to be greater than E. So the same magnitude, F, both is greater than and is less than the same magnitude E, which is obviously absurd. This is impossible. And so we can conclude that there is no magnitude greater than E, which measures both A, B, and C. So that E is that greatest common measure of A, B, and C, which is what we set out to find, which means we are therefore done with the proposition QEF. Now, much like the previous proposition 10.3, there is a porism appended to this one that likewise states that if there be some magnitude which measures 3 magnitudes, it also measures their greatest common measure, and this we found in our 8th step here, where F, because it measures A, B, and C, also measures the greatest common measure of A, B, and C, which we found to be E. Now, just as this proposition 10.4 is an extension of 10.3, we just added one more onto it, this proposition 10.4 can be extended even further to find the greatest common measure of as many commensurable magnitudes as we have. So if we want to find the greatest common measure of 4 commensurable magnitudes, we can do it. If 5, we can do it. If 6 or 7 or 10 or 20 or 100, we can do it. That's all I've got to say about this proposition, so I'll end the video here and move on to proposition 10.5.